Gracias, Edgar. Vamos a esperar unos minutos también para dar inicio. Yo estoy ya en contacto con el profesor Pat. Va a conectarse ya brevemente. Gracias, Edgar. Vamos a esperar unos minutos también para dar inicio. Yo estoy ya en contacto con el profesor Pat. Va a conectarse ya brevemente. Hi, Pat. Gracias, Edgar. Vamos a esperar unos minutos también para dar inicio. Hello, Pat. Estoy ya en contacto. Can you hear me? I think your microphone
Hi,
is...
can you hear me okay?
Yeah, it's perfect.
Excellent.
Okay. So, can we wait for a few minutes and then we can start?
Please do, because I've not opened a presentation file yet.
Okay, okay. Brevemente. Gracias, Edgar. Vamos a esperar unos minutos también para dar inicio. Yo estoy ya en contacto con el profesor Pat. Va a conectar. Wait for a few minutes and then we can start.
Please do, because I've
Bueno, buenas tardes a todos. Quiero dar inicio ya a la charla y presentando al profesor Pat Wheeler. Él es un ingeniero. Pat, I will make the introduction in Spanish, but then you will continue in English. El profesor Pat Wheeler recibió su título de grado en la Universidad de Bristol, Reino Unido. En la misma universidad también recibió su doctorado en ingeniería eléctrica. Él hizo un trabajo en el área de los convertidores matriciales. Actualmente es el director de compromiso global de la Facultad de Ingeniería, jefe del grupo de investigación de electrónica de potencia, máquinas y control y director del Instituto de Tecnología Aeroespacial, todos ellos de la Universidad de Nottingham, en Inglaterra. Es miembro de varias sociedades de la IEEE, es vicepresidente de operaciones técnicas del PELS, ha publicado más de 850 artículos en conferencias y revistas y hoy va a estar presentando la charla titulada Tecnologías y desafíos para la electrificación del transporte. So, Pat, thank you very much for accepting this invitation. And this is a talk organized by the IEEE Student Branch for this university, National University of Asunción, as well as the Faculty of Engineering. So I let you start the presentation. I think your microphone is off. Okay.
I thought it was a good start.
Okay.
Thank you very much for the invitation to come and talk. And also thank you very much for all being here. I just need to try and share my screen, which hopefully will happen.
Okay.
So, can you now see a title slide?
I don't know. ¿Le pueden permitir para compartir la pantalla, por favor?
Can you see my slide or not?
I cannot see it.
Okay, something's gone wrong.
Inge tiene acceso para compartir.
Okay. I think you have the access, Pat. Can you try again? Share. I think you have several options. All screen, one window, several windows.
So I don't use Google Meet very often.
Now I can see it. Yes.
That's better. I found something. Right. So my first apology is for the fact that my knowledge of the Spanish language is very poor. So despite visiting South America very regularly for the last 20 years, my Spanish has not yet reached a level where I can present in Spanish. So I'll present in English. I will try and speak as clearly as possible. But if there are questions, please let me know. I was going to talk about the challenges of technologies that are needed in transportation electrification or e-mobility. This has become very topical in recent years as the world tries to battle the climate change, tries to reduce our reliance on fossil fuels. And from my last visit to Paraguay, I think it's very topical for Paraguay because you're a country with an excess of clean electrical energy, mainly from hydro, and no natural energy resource in terms of gas and oil reserves. So electrification is of transportation is something that I would expect to see making a lot of economic as well as climate sense within a country in that state. I'm the head of the Power Electronics Machines and Control Group at the University of Nottingham. And this is a great privilege to be the head of a large research group because the work I present is not all my own research, it's the research done by the team that I lead. And so that's a really good way of having a good overview of all the things that are going on. Our research group currently has about 42 million US dollars worth of active research grants, and about 60% of that income is directly linked to industry. That motorbike, by the way, is fully electric. It is a race bike. It does do over 300 kilometers an hour, and that is not me riding it. I don't have quite that skill level, but we might talk a little bit more about that in a few slides' time. So my research group works in 4 technology areas. We work in electrical machines, so the design of electrical motors and generators. We work in power electronic systems. We work in motor drives and the electrical systems in which they operate. And we work in what I've called power electronic integration. That's how we build power electronics and how we define the reliability and the lifetime of power electronics. So how to build a power electronic module, but also how a power electronic module will break. So that team can tell you how and why the power supply for your laptop or your mobile phone fails and predict when it will fail. But they also have the technologies that would mean that it wouldn't fail for a lot longer time if that's what you were prepared to pay for. My academic colleagues, so the other professors, assistant professors and associate professors in each of those research areas are listed under those 4 headings. So you can see that I lead a research group with about 25 professors or academics, as we refer to them in the UK. So it's a large research group. We currently have about 65 postdoctoral research fellows, about 75 PhD students, 25 members of faculty or academic staff, and at any time, maybe 12 or 15 visiting researchers from other parts of the world who choose to come and work with us for a few weeks, a few months, or even a year. We're also very lucky in that the university sees this as a very important research area and a growing research area. And so in March 2021, just over 2 years ago, we opened our new building. So the building you can see in the picture to the top left there is our new building. It's 5,500 square meters of laboratory space, and it allows us to work up to power levels of up to 20 megawatts and voltages up to 6,000 volts DC or 11,000 volts AC. So we have a big research group. We're working in a lot of different application areas. So we're working in cars, we're working in boats and ships, we're working in aerospace, looking at aircraft, but we're also looking at the applications of power electronics in things like renewable energy and the future electricity grid, so microgrids and electrical systems, as well as a few niche areas like high energy particle physics, and where the research group started in industrial automation. So a number of different application areas, but the transportation electrification is currently about 60 or 70% of our current research projects. So the new building, as I said, was opened in March 2021. It's a nice big space. Those photos of the lab were taken before we moved in. It's now full of equipment, people, and activity. And that motorbike you can see in the lab there is also electric. And I was able to ride that down the lab before we had people in the building. So coming back to the main theme, looking at transportation electrification. I always think it's interesting to look back in history and to see what went wrong. And it's interesting when you look at electric cars, electric vehicles. The first electric vehicle was built nearly 200 years ago in 1828. So electric transportation or e-mobility is not a new idea. It's a very, very old idea. In fact, it predates the petrol or gasoline car, and was at the time seen as an alternative to steam. So burning coal, heating up water, and creating steam engines. So the peak of 20th century production of electric cars was back in 1912. So in the early 1900s, electric vehicles, electric carriages were competing with steam, not with petrol or diesel. However, by 1928, all production of electric cars had ceased for two reasons. It was because petrol cars cost a lot less and petrol cars had a greater range. The problem for us today is those problems they saw in 1828 still exist today. Electric cars are still more expensive to buy. They're cheaper to run, but they're more expensive to buy. And people still have anxiety. People are still very worried about the distance, how many kilometers they can cover before having to recharge the battery. So as engineers, it's a really good time for us because we have a problem that has existed for nearly 200 years, and we have our politicians and the supply chain and lots of the population of the world thinking that electric vehicles is the way forward, and therefore we have to solve these problems. The people are wanting us to solve them, and we have the need in terms of climate change to solve these problems. The other date I've put on there is 1839. In the UK, we sometimes believe that we invented everything. And so in the UK history books, it says that Robert Anderson of Scotland created the first electrical powered carriage. I prefer Jedlick's trolley from 1828 because I think that's probably the first thing that looked like an electric vehicle, although it would have only covered very short distances. So there's the history and there's the problem. We're trying to solve a 100-year-old problem on a 200-year-old issue. The chart in the top left there shows the roadmap by the automotive industry about quite a few years ago now, but it's still very valid. What that shows is that although electric cars will have a big place in the market over the coming decades, we might also see hydrogen, and in some parts of the world we might also see hybrid vehicles continuing to be used, particularly where we have problems with the electrical infrastructure. In the top right of this chart shows all the public electric charging points in the UK. And there are now more electric charging points for electric cars than there are petrol or gasoline stations to buy petrol or diesel. But the biggest problem with electric cars is that in the UK is we have too many cars on the road for the infrastructure we have in the country. We opened our first all-electric service station 2 years ago, and we have 100 more planned. We needed those 100 before everybody had started buying electric cars. Unfortunately, people have started buying the electric cars, and we don't have that infrastructure. So one of the things that we need to do, particularly if the UK for example, is going to meet its goal of electric vehicle only sales by 2030 is to put in the infrastructure we need to get electrical energy to the places where people want to charge their cars. And we tend to build service stations on highways in remote locations, not places where we have good connection to the electricity grid. So a lot of this is about the national infrastructure to get the electrical energy from where it's going to be created. In the UK, this is particularly wind farms, maybe some nuclear, but certainly the wind farms around the coast of the country, to the places where people want to charge their cars, particularly when we're looking at fast charging, where people want to charge quickly on long journeys. So meeting that demand of the user using subsidies and planning is critical to getting the adoption of electric vehicles. The other thing we have to remember is the technologies that I'm involved in around electric motors, power electronic converters, and the whole drivetrain that we need in electric vehicles. If we can make the electric vehicles more efficient, we can make them lighter, we can make them more fun to drive, these are things that will help the market to grow and help people to move towards electric transportation. It's not just about cars. Another area that we work on is electric aircraft. So when we're looking at aeroplanes, we see that we have, at the moment, we use aviation fuel, we use a lot of that, and we've been looking for the last 10, 15 years at how we can make the propulsion of an aircraft electric. This is something the aviation industry has been looking at because they have a goal to reduce the CO2 emissions, for example, by 2050 back to the level that they were, or half the level that they were, in 2010. By 2040, they should be at the back of the 2010 level. So that's quite a lot of reduction, particularly when you consider that if the industry took no action and just allowed the aircraft industry to grow, we would have over twice the CO2 emissions that we had in 2010. So we need to reduce the CO2 emissions from aerospace by a factor of 4 over 40 years. One of the things you have to remember is that an aircraft typically lasts 25 or 30 years. So the aircraft that are being bought today may still be flying in 2050. So we've got to insert new technology very early to try and meet these goals. And you've seen that with things like the Boeing 787, an aircraft which is far more efficient, far lighter, and has far more electrical technology on it than ever before. The good news about this roadmap is that we've already done some of this work. The yellow or gold area on that chart are known technologies that we can already deploy. The green area is where we need the technology development. And one of the ways we might do this is by making the aircraft propulsion electric. So this is a NASA roadmap of how that might happen, getting steadily larger and larger electric motors on the wings of the aircraft as fans to propel the aircraft through the air. When we're looking at 1 or 2 seats, we can do that today, and the motors are 10, 20, 30 kilowatts. By the time we get to large passenger aircraft with 300 or 400 people, we're looking at 10 to 20 megawatt motors that we need to design and build. We also need the power system and the power electronics to control them. So it's a good time to be an electrical engineer. There's plenty of challenges. What the chart on the top right here is showing is that same trend of aircraft getting slowly larger over the next 3 or 4 decades. And on that, we've superimposed the electric motors that we've built and tested in our labs at the University of Nottingham. So the largest we've built and tested to date is 4 megawatts. And that motor is big enough to drive the fans on a regional aircraft, an aircraft with maybe 100 passengers. So we've got the technologies, we've got the motors and the power electronics to be able to demonstrate that we should be able to meet the requirements of these aircraft. You'll notice that the curve of the electric motors is steeper than the curve of the electric aircraft. The reason for that is that as the aircraft get larger, the time it takes to design and build a new aircraft gets longer. So we need to have a larger and larger gap between the technology and the aircraft actually flying with passengers. We haven't solved everything yet. We can build electric motors with the right lifetime. We've got the efficiency nearly where it needs to be. Power density, we've got some work to do on that, but the biggest area is cost. At the moment, the technology is too expensive. So we've got a lot of work to do on working out how to manufacture the power electronics and the electrical machines to meet the cost point that we have here to make all these systems viable. One thing to remember if we're going to fly in electric aircraft is that they're not going to be battery powered for long flights in the next few years. We're going to have to go through a phase of having hybrid systems where we have some sort of gas turbine or maybe a hydrogen fuel cell, but we have some source of electrical energy that we put onto the electrical bus. We then convert with our power electronic converters into our electrical motors to drive the fans. This gas turbine shown on the right hand side here though, that doesn't need to be on the wing of the aircraft because the connection between the gas turbine and the electrical fans is now electric. That big gas turbine can be behind the passengers in the body of the aircraft rather than on the wing of the aircraft, creating wind resistance and loss of efficiency. So to get a more efficient aircraft, we can do that using electric propulsion, and then we can design our gas turbine so that it spins at only one speed and only one power point. And by doing that, we allow the mechanical engineers who design the gas turbine to design a more efficient gas turbine. And therefore, the whole fuel usage of the aircraft will reduce. This is particularly important if we want to run that gas turbine on something like hydrogen rather than on the specialist fuels we have today. So we're going to go through this phase where short haul aircraft flying between cities in one country might be all electric using batteries, just like the electric car. But aircraft that are flying longer distances are going to rely on things like fuel cells or gas turbines. But those sources of energy are going to be in the body of the aircraft along with the passengers. And we're going to use electric motors on the wings of the aircraft that are smaller and lighter. And by doing that, we get a more efficient system. So I'm a professor of power electronics, so I have to have at least one slide in here about power electronic converters. Whenever we have these systems, we have lots of power electronic converters in there, but we have lots of different power converter topologies. And so we need to think about which power converter topology is the best for each application. There's no right answer. This is not like an exam question. Every power converter has advantages and disadvantages. And power electronics has gone through a very exciting period of change in the last 5 years. We used to build all our power electronic converters out of silicon IGBTs or silicon MOSFETs. But two new materials have come along, silicon carbide and gallium nitride. And those two semiconductor materials have changed everything. The frequencies we can switch at, the way we operate the power converters, and the losses we get from the power converters have all changed. We're switching at far higher frequencies and the losses have come right down. So 10 years ago, I would always say a very efficient large power converter might be 97% efficient. Now it's over 99% efficient. So the losses have come down and the size and the weight has come down. And you can see that on this graph here. This is just a design example where we looked at building the same power electronic converter from silicon carbide, SiC, MOSFETs and silicon IGBTs. And we looked at the volume of the filter we would need on the power converter and the converter losses. And as you can see, as we go up in switching frequency from 10 kilohertz to 80 kilohertz, the losses in the silicon IGBT converter, the red line on that curve, more than double. The losses in the silicon carbide MOSFET converter, shown in blue, only go up by maybe 20%. So I can build a very small, compact power converter out of silicon carbide because the heat sink I need to dissipate that power loss is going to be very small, and I can make the switching frequency higher to reduce the size of my filter components. So this has been a very exciting time in power electronics because we're suddenly able to do things we could never do before. As I said before, there is no one power converter that has the perfect the perfect setup. All power converters have advantages and disadvantages for different aspects of their operation and their construction. So as you can see there's lots of lows, mediums and highs, and we have to choose the power converter topology that suits our application the best. That's again good news for us as power electronics or electrical engineers, because to make those choices requires the skill of an engineer. The final picture I have here is looking at the size and the weight of power electronic converters and how we can make those smaller and lighter. And I'm always asked to predict what the power density of power electronic converters is going to be in the future. So I've made a prediction, and that prediction has a very wide variance of what happens in 20 or 40 years' time. And the reason for that is very simple. And when we build a power electronic converter, if we build it in its own box with its own heatsink and its own structure around it, then there's a limit to how small and light we can make that. You can see that with your laptop power supply. Your laptop power supply has been about the same size for the last 20 years. They build those power supplies at a particular cost, but they also build it as a standalone power supply. If they built that power supply into your laptop, it would be a lot smaller because it would use the structure of the laptop, it would use the body of the laptop as a heatsink and so on. And so you would be closer to the blue line in terms of the power density rather than the yellow line. So what I'm trying to say here is that power electronic converters will continue to get smaller and lighter. That's really good news for transportation electrification, because that means more room for passengers in the aeroplane or in a car. But it's that integration of the power electronics with its application that is really going to make things so much smaller and lighter. It's a little bit the same for electric motors. When we look at what's happening in electric motor design, we find there's lots of new technologies. Power electronic converters is one. Understanding the cooling, the thermal design is another. New materials, both for windings and rotors and stators is another, so the magnetic materials. And advanced machine designs, particularly using 3D printing or additive manufacture, are having big impacts in the research environment. And it's always good if you have lots of new technologies, to look at what impact they're going to have in the application. So this is looking at various technologies and the impact they're going to have in transportation electrification. Technology readiness is how ready is that technology to go into an application. So on the right-hand side here, you can see things like new magnetic materials. They're very advanced technologies. I can go and buy those. I can use them today. They're going to have a small impact on the size and the weight of systems, but it's acceptable to be able to use those. Wide bandgap semiconductors, the green circle on there, are having a very big impact on the size and the weight of systems. They're not as high in technology readiness level. We're still developing those ideas. If we look at the new technologies that are coming along, but they're at very low technology readiness level, we couldn't put them in a product today, but we might be able to in the future. We see things like superconductivity and additive manufacturing. And those are technologies which will have a big impact on the size and the weight of transportation and electrification systems, but a lot more effort is needed to develop those technologies to the point where we can actually use them in a commercial product. So it's interesting there to look at impact and technology readiness level. Finally, in this talk, I just wanted to have a quick look at electric superbikes. We do a lot of work in Nottingham with the car industry, the automotive industry, but they're an industry that doesn't like us to talk about the research. But with my students, we've built an electric superbike to go racing. And we can talk about that because that is our technology. We've designed it, we've built it, and we race it. So this motorbike is capable of speeds up to 300 kilometers an hour. It has a peak power at the back wheel of around 200 kilowatts. And before the pandemic, we were racing in the Isle of Man TT, and we were always finishing on the podium. This motorbike is faster around a Formula One racetrack, such as Portimao, than a standard superbike. So we've done side-by-side testing with the same rider on the same day, with the same familiarity on the electric superbike and on a BMW superbike. And we were 2 seconds a lap faster on the electric bike. So this is a race bike. It's not designed for the road. It's designed for racing. We do this for a number of reasons. I believe as a university, we have a duty to educate people and to raise awareness of new technologies. And racing electric bikes is a very good way to get TV and media coverage. We can also push the boundaries of technologies. I had a PhD student who designed an electric motor around the requirements of the motorbike. And he finished doing his testing work in the laboratory on a Friday. And by Saturday afternoon, we were racing the bike with his motor on that bike. You can't do that in a production car, but you can when you're racing. And it also allows us to test new ideas and to challenge regulations and to really bring the technology forward. For those of you who have never heard of the Isle of Man TT, you can look this up on Google. In fact, the racing at the Isle of Man will be next week. The Isle of Man is a small island off the coast of England. It has its own government, and for 2 weeks each year, they close the roads on the island to create a 60-kilometre, so 60 kilometres or 38-mile track, which is not really a track, it's roads. It's just the small roads around the island. And they race bikes on there every year. It is the most dangerous and most testing place to race motorbikes in the world, and it's been happening for over 120 years. So a very challenging place to be and very good fun. Why did we choose that place to race motorbikes? Well, if we can race there, we can race anywhere. When you look at the electrical system of our motorbike, it's very simple. We have a battery pack. So I need some batteries to provide the electrical energy. I then have a power electronic converter that is acting as the motor drive, shown in blue. That controls the electrical motor, shown in orange. And then we have a single chain that goes to the rear wheel. There is no gearbox, we don't need one. There's also a display, but the rider of a race bike will never look at the display. That's only for testing purposes. And it's a control loop with one input, and that is the torque, the throttle, the accelerator. So how much torque do I want the back wheel to provide? Now, this leads to an interesting problem for transportation and electrification. The thing that restricts the speed of our motorbike in that race at the Isle of Man is not the motor, it's not the power electronics, it's the battery. It's the amount of energy I have on that motorbike. And we can see the problem here. If we look at energy density and power density, we can see that a gas turbine engine or a petrol engine has far better power density and energy density than any of the competing technologies. In terms of energy density, fuel cells, including hydrogen fuel cells, are not too bad, but they lack power density. Capacitors are good on the power density, but they're not so good on energy density. You end up needing lots of batteries if you want to store lots of energy. And that's why we find ourselves using rechargeable batteries. Now, battery technology has developed with time. We had lead acid batteries, we had nickel cadmium and nickel metal hydride batteries, and then we had lithium based batteries. What history tells us is that battery technology changes and evolves, and every time it changes, every time we change the chemistry, we get better power density and better energy density. So what that suggests is that in the future, there will be a different battery chemistry, and it will be approximately in that red circle on the chart there. And that when we get that technology, we will be recharging our mobile phones once a week, not once a day. And all that anxiety we have about the range of our electric cars will disappear because we will be able to store more energy in a smaller space, but almost as good as the gas engine. I don't know what that chemistry will be. If I did, I would be very, very rich and probably buying Twitter off Elon Musk. I don't know. I suspect it will be sodium, but that's only a thought. At Nottingham, we like to demonstrate things. So just to finish this talk, here's a case study. This is looking at a hybrid engine for a regional aircraft, a type of airplane with maybe 100, 120 people. And we designed the power electronics and the electrical machine to wrap around the gearbox on the shaft of an existing turboprop engine. So this is to be able to boost the power of that engine for things like takeoff. It's to be able to move the aircraft on the ground by spinning the propeller, but not using the engine itself when we're taxiing. And by doing these things, we can put a smaller engine on a larger aircraft and get an increase in efficiency. Problem with this is that it's a very harsh environment, high temperature, 130 degrees centigrade, lots of vibration. And my power electronic converter had to have the shaft going to the propeller running through the middle of the power electronic converter. So rather than having a nice square box for my power electronics, I had to design, well, my researcher had to design power electronics that are in a circle with a hole in the middle. Not so difficult for the motor, but quite challenging for the power electronics. And this is what I mean by integration, or the early stages of integration, because the power electronics and the motor are cooled by the same coolant as the gearbox and the turboprop engine. So to conclude, transportation electrification or e-mobility is happening. Power electronics and electrical machines are key technologies. Energy storage systems must improve. One of the problems we have with electric transportation is this anxiety about the range and the weight of battery systems. So we need that step change in battery technology. And electrical power networks in our countries will require significant investment in transmission, distribution, and renewable generation systems if we're going to create the electrical energy that is needed for these systems to work. I hope you found that useful. I hope you found it interesting. And I'm very, very happy to take questions. I believe you can type those into the chat if you wish, or raise your hand. I'm not sure how it works. But thank you very much.
Okay. Thank you very much, Pat, for your presentation. It was very interesting. So now we have time for questions. I already have one, but as you already mentioned, here in Paraguay we have an energy excess that typically we always discuss what we can do with that for the past, I don't know, 10 years, and still now we still discuss about it. So what can you suggest about it? What do you think about what we can do regarding this energy excess?
Well, I think Paraguay is one of those very few countries that has an excess of electrical energy. I'm aware that you generate a lot more electrical energy than you use as a country. That's quite unique in the world. So, but it's quite a long way away from your main cities. It's up in the Agasu and places. So I think there's a need for Paraguay to invest in the electrical infrastructure so that it can actually access that electrical energy in the big cities. But the other thing to do is to make sure that as a country, if you have that desire to use more electric vehicles, that you make sure that infrastructure for charging those vehicles is available at the places where people are going to want to charge them. One of the things we noticed in the UK is that people will fill their petrol tanks with gasoline, with petrol at home, near where they live, and then drive a long distance. Whereas with electric cars, they will charge them on those journeys. They'll stop, have a cup of coffee, and expect a fast charger to be available to charge the battery up in the 20 minutes it takes to have a cup of coffee. And that means you have to change the way the infrastructure works. And there's some good commercial reasons for doing that. Having people stopping on a long journey and wanting to buy food and drink is a good commercial proposition. But you've got to have the ability to charge those vehicles whilst they're doing that. And so that's making sure that you have the policies in place, but also making sure those policies include getting the electrical energy to where you need it to charge the vehicles, and making sure that electric vehicles are always going to be more expensive to buy, but the running costs and the servicing costs are very low. An internal combustion engine has a lot of moving parts, and that's why there's a big industry around servicing existing cars. When you have an electric car, it's a very simple system, and all those jobs like changing oil and changing parts on a petrol engine all disappear. Good power electronics and electrical motors need servicing every 10, 15 years, not every 12 months. And also you don't use the brakes because you use regenerative energy. So you're down to those places just doing things like replacing tires and maybe just checking that everything is tight and safe, but they don't have the same amount of work as they're going to do today. So the cost of using your car goes down, but the cost of buying it will go up. Sorry, that was a long answer.
That's actually, you answered another question that I already had.
Okay, so
Yeah, I have another one. I don't know if people have any questions. One of them is related to the research. I think you said that around 60% of your research budget came from the industry, and this is actually here in Paraguay is quite difficult, or I don't know. That's my question. How what do you suggest we can do in a country like Paraguay, a developed country? I think that you may know other countries like here where it's very difficult to get the support for the industries.
well, one of the things, what the slide actually said was 60% of our income is associated with or connected to industry. One of the things our governments do, both in the UK and in Europe, is to have funding schemes where industry puts in money to a project and the government puts in money to the project, as long as there is a technology provider in that project. So you end up with a project with industry and universities working together, funded half by the industry and half by the government. Industry likes that because it's doubling its money. We like it because we get some interesting projects with industry and we get impact from our research. And why is it important? Well, there's always a technology risk. When you're introducing new technologies in industry, that's a big risk. And the purpose of that government money is to enable industry to take that risk, to be able to invest in new technology, but not risk the entire business on that investment. And that's where government should be stepping in and supporting its industry, is to actually enable industry to take those risks. If there's no risk in that type of project, it shouldn't be funded by government. It should be funded by the industry themselves. But it's the bit where they're working with universities and getting that transfer of new technology. To my mind, government has to help with that level of risk.
Perfect. Thank you. I think there is one question from Andres.
Yes, thank you for the question. Yes is the answer to that question. It's a complex question, but there are a number of research groups, including at my own university, looking at various technologies. Some of the most promising ones at the moment are around sodium, particularly sodium air, but there's some other sodium chemistries as well. Now, that's quite interesting because a lot of people have got a lot of money invested in lithium. So what we will see is those new technologies looking very promising, but it'd be quite hard. It's going to take a lot of investment for those to actually become the dominant technology. Sodium air is an interesting one to me, because if you take a lithium-based battery, it always has a voltage across the terminals. So there's always energy stored in the battery. So whenever you're transporting it, there's always a risk of fire. The sodium air battery has the advantage that you can actually totally discharge it and short out the terminals. So there's no stored energy, and you get a far greater, it's far safer in transportation when it's not being used. And so for that reason, and for the fact it has a slightly better power density and energy density, it is one that I quite like. But I can't convince myself it's actually the one that will win the will win the technology argument. But yes, those technologies are there, and people are working on those. There's a question about wireless charging. That's always a very good question. We're actually looking at it at the moment for railways as an alternative to overhead lines. What wireless charging does for you is it makes it a lot more convenient to charge your vehicle. If when you park your vehicle at your house or in a car park, there is a facility there to allow wireless charging of your battery, then obviously that's far more convenient than having to use wires and plugs and sockets. The problem with wireless charging is that it's not as efficient. Static charging has one level of efficiency. If you go to dynamic charging, where you charge when the vehicle is actually moving, then the efficiency gets worse. A connection where you have copper connected to copper in a connector with a wire is always going to be more efficient. So you're trading off the cost of the energy against the convenience of the user, and you have to decide whether that is worth it or not. One of the places I see wireless charging may work well is, for example, buses and trains which stop regularly. So if you think of a bus in a city stopping at particular locations as passengers are getting on and off, it's going to be doing that repetitively, and you don't have time to connect it physically to the supply. And therefore, topping up the battery with energy using wireless charging might be economically sensible because it's more convenient. Your car that you drive to your place of work or study, it's easy to plug that in and let it charge over time. That's not such a problem. So it's that issue of convenience against efficiency that we'll see. And so you will see wireless charging, but you won't see it, in my mind, you won't see it on all vehicles because it will never be as efficient as a hard wired connection. Very good question, though.
Okay, thank you very much. But I think we can close the question round. And I thank you again, Pat, for your presentation, your time, and as you always help us a lot. Not only this group, I know you know a lot of Paraguayan people. So thank you again.
No, thank you very much for the opportunity to speak, and I hope you found it interesting. If you do have questions later, do drop me an email. You'll find my email online very easily. But thank you very much for the invitation, and I look forward to meeting some of you in the future. Thank you.
Thank you, Pat. Bye.